Good evening, class. So let us start. Have you watched week 9 videos?
Not yet, ma'am.
Okay, Abhay and Pawan, 50%. All right. Okay. So I will, try to summarize some of the things discussed here. And if you like want detailed derivation or, how that property came, and also I will request you to watch the lectures. Um, so let us start. So in week 9, in the first lecture, Fourier series was summarized. So I will also do it quickly. So we'll start with summary of Fourier series. Why am I doing this? Because we can, see some kind of analogy and similarity between the Fourier series and Fourier transform properties. So in Fourier series, we decompose a periodic signal in terms of phasors. So Fourier series involves decomposition of a periodic signal in terms of phasors. Phasors were e raised to the power of j k omega t. They are eigenfunctions of LTI systems and hence convolution, and also Fourier series. And we saw it while we studied Fourier series. So Fourier series is decomposition of a periodic signal in terms of its phasors. And now I will write the expression for the Fourier series and the Fourier series coefficient. So Zt, which is a periodic signal, is given by summation k equal to minus infinity to infinity ak e raised to the power of j k omega t. Omega here is the fundamental frequency. K is an integer. So k omega will be the harmonics of this frequency. And ak here is the Fourier series coefficient. So I'm just writing it as FSC, which is Fourier series coefficient. And ak is given by 1 upon t. Integration is done in an interval of t, where t is the period of the periodic signal zt. So e raised to the power of minus j k omega t. Again, k is the same integer and omega is the fundamental frequency. So this is what was the Fourier series and the Fourier series coefficient. So it has phasors of a fundamental frequency and its harmonics. Phasors of a fundamental frequency and its harmonics. So, do you recall Gibbs phenomena?
Yes, ma'am.
So, Gibbs phenomena occurred when infinite phasors were required for the representation. Infinite phasors may be required for representation. So, like when we have, square wave, then to represent this, we need infinite phases to get, these sharp edges and all of that. So, Gibbs phenomena comes into picture in such cases when infinite phases are required for the representation. And spectrum and bandwidth depend on the frequency components present. spectrum of the signal and bandwidth depend on the frequency components present. So spectrum and bandwidth depend on the frequency components present. Then we had Parseval's theorem. So when we have a Fourier series, then first of all, power or energy in any representation, that is whether time domain or frequency domain, power and energy in any representation are equal. So the power of a periodic signal that we can also calculate using the Fourier series coefficients, which is done in the following way. So power energy in any representation are equal. So power of a signal Z will be summation k equal to minus infinity to infinity mod of ak squared. So ak was the Fourier series coefficient of the signal zt. We take the Fourier series coefficient, take the modulus, square it, and then add for k varying from minus infinity to infinity, that is all of the frequency components, and we will get the power. Next, we also studied about Dirichlet conditions. So, Dirichlet's conditions ensure existence and convergence of Fourier series. Dirichlet conditions ensure existence and convergence of Fourier series. So, do you recall Dirichlet's condition?
Yes, ma'am.
Okay. So, according to this, our time domain signal, so there are three of them. For the time domain signal, it should be absolutely integrable in one period. It should have finite number of discontinuities in one period. It should have finite number of maxima and minima in one period. If these three conditions are satisfied, then we can say that the Fourier series exists and it will converge. So I'll quickly write them down. The time domain signal should be absolutely integrable in one period. So in all of these three conditions, we are taking in one period. Should be absolutely integrable in one period. Then should have finite number of discontinuities in one period. So you remember na, the function of the definition of continuity. We say that a function is continuous when the limit exists, that is the left hand limit is equal to the right hand limit, and that limit is equal to the value of the function at that point, then we say that it is continuous. If these are not satisfied, then the function is discontinuous. So if in one period our time domain signal should have finite number of discontinuities. And the third one was should have a finite number of maxima minima in one period. Then next, when we say frequency response, Then, in with respect to Fourier series, frequency response is the eigenvalue of the LTI system corresponding to the phasor of the given frequency. So, if I have, this kind of output, then this signal, this one, and this is the phasor of frequency k omega, and this lambda of k omega is the eigenvalue or the frequency response at this frequency. I will write it down. Frequency response is the eigenvalue of the LTI system corresponding to the phasor of the given frequency. Corresponding to the phasor of given frequency. Here the frequency is k omega. So this lambda k omega is given by integral from minus infinity to infinity h of t e raised to the power of minus jk omega t dt. So here h of t is the impulse response of our LTI system, and this integral is the eigenvalue or frequency response. Are things clear till this point?
Yes, ma'am.
Okay. Then when we multiply two signals, when we multiply two periodic signals, then it results in the discrete convolution of their Fourier series coefficients. Multiplying two signals results in discrete convolution of their Fourier series coefficients. And then, uh, if we have an even signal, for even signals, Zt is given by B naught plus sigma k equal to 1 to infinity bk cos of k omega t. So we have the DC component B0 and phasors from 1 to infinity which have cos in them. So cos is even. And when we have odd signals, then Zt is sigma k equal to 1 to infinity bk sine k omega t. So here sine is an odd function and the DC value is 0 because for odd signal, like if zt is odd, then it should be equal to minus z of minus t. So at the value at t equal to 0 has to be equal. Sorry, has to be 0, otherwise they will not be equal. So that is why DC component is not there for odd signals. Now I will quickly write down the properties. So here we have Zt, which is a time domain signal, and Ak, the Fourier coefficients. So if Zt is even, then the Fourier series coefficient are also even. If Zt is odd, Ak is odd. If Zt is conjugate symmetric, Ak is real. If Zt is conjugate asymmetric, Ak is imaginary. And if Zt is real, then Ak is conjugate symmetric. If ZT is imaginary, then AK is conjugate asymmetric. So there is, like if one is even, the other is even. If one is odd, the other is odd. If one is conjugate symmetric, the other is real. When one is conjugate symmetric, the other is real. If this is real, this is conjugate symmetric, and so on. Now, next we have the conjugation, reversal, and other properties. So I'll make another table for that. ZT, time domain, AK again, Fourier coefficients, and next we have bandwidth, whether it changes or not. So, if we conjugate the signal in time domain, then the Fourier series coefficients are reversed and conjugated. Both the things happen. Bandwidth does not change. Now, z of minus t, that is, we time reverse the signal. Then the Fourier series coefficients are also reversed. Again, bandwidth does not change. Z of t minus s. So, ak e raised to the power of minus jk omega s. I can make it plus minus. So, that is how it is. So, here only phase changes. Magnitude does not change because the magnitude of e raised to the power of jk omega s is 1 only, right? Again, the bandwidth does not change. Then we have Z of Ct, time scaling. The Fourier series coefficient AK becomes A of K by C, and if C is greater than 1, then bandwidth expands. In the frequency domain, there is expansion. And if it is less than 1, then it shrinks. So I want you to look at this last property. So here, if the Fourier series coefficient of Zt was ak, then Zt has a of k by c. But this happens when my fundamental frequency remains the same. You might recall it from maybe the previous or previous to previous week. So when the fundamental frequency remains same, then we have this. But when the fundamental frequency changes, then the Fourier series coefficient remain the same. I think we had one problem related to this also. And another thing I want you to notice is here when C is greater than 1, then C greater than 1 means compression here. Compression here, compression in time, expansion in frequency. Expansion in time, compression in frequency. So uh, the opposite things happen in these domains. If in one domain there is expansion, then in other domain it shrinks, and so on, vice versa. So this was the summary of Fourier series. Now we will start with Fourier analysis of aperiodic signals. Things are clear till this point now.
Yes, ma'am. If there is any question like z 5t minus 3, so that 5 should reflect in that ak divided by 5 also, right?
Will you please repeat Z of
5t minus 3.
5t minus 3?
Yes,
So,
so
so here two things are happening. Shifting also, scaling also. So you will have to take both these properties into account.
okay.
Fourier analysis of aperiodic signals. So remember we had that periodic rectangular wave and then we found out its Fourier series coefficient. Do you remember? Anyone remembers?
Yes, ma'am.
Okay, I will draw it here. This t by 4 minus t by 4, t by 2 minus t by 2, and then it repeats. So the time period here is t, and this is 1. So for this signal zt can be written as summation sine k pi by 2 upon k pi into e raised to the power of j k omega t. This is just the Fourier series expression zt is equal to sigma ak e raised to the power of j k omega t. So here this thing sine k pi by 2 upon k pi is ak. Now we will look at this same expression with the duty cycle included. So let us first see what duty cycle is. So duty cycle is the ratio of time for which signal is non-zero upon total time period. So let us look at this rectangular wave. So the time period here is t. So in denominator we have t. Now in numerator, time for which signal is non-zero. So the signal is non-zero in this duration from minus t by 4 to plus t by 4. So when we calculate the duration, it will be t by 4 minus t by 4, that is t by 2 upon t, which is 1 by 2, which is zero point 0.5, or we can say 50%. So this is 50% duty cycle. So the definition of duty cycle is clear, and how it is 50% for this particular case.
Yes, ma'am.
Okay, now let us shrink this. So I'm just considering one time period right now. I will just draw it. So this time period is the same, minus t by 2 to plus t by 2, but now instead of t by 4, I have made it t by 20. So let us see the duty cycle. So this duration for which the signal is on is t by 10, right? Class, this is clear na how the time for which the signal is on is t by 10.
Yes, ma'am.
Okay, now the time period is still t. So now I have 1 by 10, which is zero point 0.1, or this is 10% duty cycle. Now what we will do is we will calculate that AK, which was this, with the duty cycle factor included. So let us do it. So AK is just the definition of the Fourier series coefficient, 1 by t integration over t zt e raised to the power of minus jk omega t dt. Now what I am saying is 1 upon t, and this for which the duration in which zt is 1, that actually becomes minus dt by 2 to dt by 2. So let us verify it for this 50% case also and 10% case also. So, okay, I will do it inside this box. Now, when for the first case, duty cycle D is half, right? So D is half. So dt by 2 will be how much? T by 4, right?
Yes, ma'am.
Now let us take this second case. So here D was 1 by 10. So dt by 2 will be
T by
T by
20.
20. So that means dt by 2 here is giving me this, right? The times for which it is on. So I changed the limits from, I took it from minus dt by 2 to dt by 2. The time period is t, and in this d minus dt by 2 to dt by 2, this is 1. 1. So I will write 1 e raised to the power of minus j k omega t dt. Let us quickly solve this. So 1 upon t e raised to the power of minus jk omega t, and in the denominator we have minus jk omega. The limits are dt by 2 minus dt by 2. The negative sign will flip the limits. So I'm going to absorb the negative sign there. Now let us substitute this. 1 by t e raised to the power of j k omega d capital T by 2. The minus signs cancel, then the lower limit minus j k omega dt by 2 upon j k omega. Now, what I want to do is I want to write this thing in terms of sine. So, you know, na, sine theta is equal to e raised to the power of j theta minus e raised to the power of j theta minus e raised to the power of minus j theta divided by 2j. You know this now.
Yes, ma'am.
So that I will use here. So I need 2j. So I will multiply and divide by 2. So 2 here, 2 here. So I have 2 by t sine of k omega dt by 2 upon k omega. Now, what I will do is omega is equal to 2 pi by t, relation between the angular frequency and time period. So I will replace omega by uh, t. So 2 by t sine of k, 2 pi by t dt by 2 upon k, 2 pi by t. Now we have some cancellations here. 2 dt. So what I'm left with is sine of k pi d upon k pi. So now we have the Fourier series coefficient with this duty cycle factor d here. So I just wanted to show you this. And another thing I would like to show is the following. So in one case, omega is 2 pi by t, and in another case, okay, I will just draw the waveform once more. My network connection was not very good today, so if I'm not audible or something, please let me know. So minus t by 4, amplitude is 1. Now I will call this n times of t, and this minus nt. I will take one example for n equal to 10. So the first case, omega is 2 pi by t, which is the case we started with. That is this, the pulse in blue. Time period was t. It was on between minus t by 4 to t by 4. So that is the one case for which I've written this omega. Now let us take omega dash, which will be 2 pi for this case. So time period will be 2 times nt here. This is clear na? Time period is 2 nt here.
Yes, ma'am.
So that is what I did. Now I will put n equal to 10 here. So 2 pi divided by 20t. Now we got this Fourier series coefficient, and this is like a sinc function. Have you studied about sinc function in any of the previous weeks?
Yes, ma'am.
All right. So this is a sinc function. So in time domain, it was rectangular pulse. In frequency domain, it is a sinc function. So I will draw it here for both of them. Now here omega is 2 pi by t. So we have some components like this. So in the first case, we have components like this. And can you see that omega is greater than omega dash? Are you able to see this? Omega is 2 pi by t. Omega dash is 2 pi by 20t.
Yes, ma'am.
In omega dash, the denominator is higher. So omega dash will be lower. So omega is greater than omega dash. So for omega, we have this certain kind of the spectrum. But for omega dash, since omega dash is smaller, so here we will have them at k omega, and here k omega dash. So k omega will be greater than k omega dash. So here this gap was more, but in the omega dash, k omega dash, the gap will be less. So we will have more points here compared to the omega one. So in the second one, it the spectrum has become more dense. AK is uh, discrete now, so it is at discrete values. It is not continuous. Here the gap was more. Here the gap has decreased for the omega dash case. So that is what I wanted to show you here. Now if we come back to this waveform over here, so here if we make t tending to infinity, so this will be from minus infinity to infinity. So our signal will become aperiodic. Only one period we will have. So if t time period tends to infinity, then only one cycle is left. This you're able to see now, that if t tends to infinity here, then only one cycle is left.
Yes, ma'am.
So only one cycle is left. Now my signal has become aperiodic. It is not periodic anymore. So t tending to infinity, or since it was nt, so n tending to infinity. So what we saw was, here, as here the n was 1, here n was 20, so this was denser. So as n tends to infinity na, so it will become like a continuous plot. So this thing in blue now, it will become continuous like that, instead of these discrete points in pink. So when n tends to infinity, it is more and more dense, like a continuous plot. So when you watch the lecture now, from this periodic signals and discrete thing in frequency, we are going to continuous thing in frequency, and we will eventually get to the Fourier transform. So for all that derivation, you can refer to the professor's lecture. And this one, the value of integral, which is from previous weeks, I would just like to write it over here. Integration minus infinity to infinity e raised to the power of j omega minus nu t dt. The value of this integral comes out to be 2 pi delta of omega minus nu. That is, if nu is not equal to omega, then the integral is 0. And when nu is equal to omega, this is what we have. So this now comes from the orthogonality and inner product that we studied. That is, if we take this phasor e raised to the power of j nu t, e raised to the power of j omega t conjugated dt from minus infinity to infinity. So this was something that we did for orthogonality, and that is what is written here, which integral evaluates to this 2 pi delta omega minus nu. Now we will move to the Fourier transform definitions. This is clear now, that how when n tends to infinity, then the spectrum is becoming more and more dense, like a continuous plot.
Yes, ma'am.
All right. Now let us come to Fourier transform definitions. So if I have a time domain signal xt, continuous time signal xt, its Fourier transform is denoted by x of j omega, or I can also say that x of j omega, the inverse Fourier transform of x of j omega is x of t. Let us define the Fourier transform here. Ft is for Fourier transform. So x of j omega, the Fourier transform is equal to integral from minus infinity to infinity xt e raised to the power of minus j omega t dt. So this is my definition of Fourier transform. IFT is inverse Fourier transform. I will define it here. X of t is equal to 1 upon 2 pi integration from minus infinity to infinity x of j omega e raised to the power of j omega t d omega. So this is the Fourier transform. This is the inverse Fourier transform. Now I will write Parseval's theorem. These definitions are clear now, what I have written.
Yes, ma'am.
Now I will define Parseval's theorem here for these aperiodic signals. So majorly na in Fourier series coefficients, in Fourier series, we had periodic signals. So periodic signals are power signals. So we had computed power there. Now here when we come to Fourier transform, xt is aperiodic. So in general, they are energy signals. So here we will be computing energy. So Ex is, this we knew from the earlier weeks, that when we want to find the energy of a signal, we take its mod, square it, then integrate from minus infinity to infinity. Now, in with respect to Fourier series, Fourier transform, with respect to Fourier transform, we can write it as 1 upon 2 pi. Again, how this comes, you can refer to the professor's lectures. 1 upon 2 pi integration minus infinity to infinity x of j omega. X of j omega was the Fourier transform of xt, right? X of j omega was Fourier transform of xt. So that is what we took here. So x of j omega, we take its mod, square it, integrated with respect to omega. 1 upon 2 pi integration from minus infinity to infinity mod of x j omega whole square d omega. So these are equal, and we can write it as E of capital X by 2 pi, where E of capital X of j omega, you can skip this j omega also. So this is capital X. This one over here, this is capital X, and this is small x, the time domain signal, the Fourier transform. So E of capital X of j omega will be same, just the definition for the energy, take the mod, square it, integrate it. So this is equal to Ex divided by 2 pi. So this is the Parseval's theorem here. The definition is clear.
Yes, ma'am.
Is there any doubt, Ananya?
Ma'am, it's little not clear. I think it's because I haven't watched lectures.
So you remember this thing, the definition of how we calculate the energy of a signal.
Yes, ma'am.
Now what I am saying is, suppose I have this Fourier transform, that is another signal. So the energy of that signal will be this. Can we say that?
Yes, ma'am.
We are calculating the energy of this. We take its magnitude, square it, and then integrate it, just like we did for xt. So this is clear.
Yes, ma'am.
Now what I'm saying is that this is in time domain. The relation between them is uh, E of capital X divided by 2 pi. So these energies are related like this. If I have a time domain signal, I want to find out its energy, I can use this. But if I know its Fourier transform, and if calculating this integral is easier for me, so I can calculate it using this. If this happens to be easier, I can calculate it using this. So this is just the definition that I wrote, that this energy is also equal to this.
Okay, got it.
Okay, now the next thing is uncertainty principle. So here we will take a rectangular pulse in time domain, calculate its Fourier transform. Then we will take a rectangular thing which, okay, let us see it as we go into it. And the next thing is the uncertainty principle. So now I am taking a rectangular pulse and time domain, which is this. So this is between minus t naught by 2 to plus t naught by 2, it is 1, and outside it is 0. So can someone tell me the expression for this? Like, how do we write in terms of the rect function? It will be rect
That
of, yes, speak Ananya. It will be rect of t by t naught. So this is how we define the rect function. Na? Rect of t by t naught analytical. This is the analytical expression. Graphically, this is what we have. So now we have this rect function in time, and we want to find out its Fourier transform. So let us do it. The definition of Fourier transform is x of j omega is equal to integration from minus infinity to infinity xt e raised to the power of minus j omega t dt. So this is the expression for the Fourier transform. Let us now calculate the Fourier transform. So xt is 1 between minus t naught by 2 to plus t naught by 2. Outside it is 0. So my integral becomes minus t naught by 2 to t naught by 2. Here xt is 1 and this stays as it is. Now I have to find this integral. E raised to the power of minus j omega t as it is. Minus j omega comes in denominator. These are my limits. I will absorb this minus sign in the limit, so the limits will get flipped. These properties of integral, I'm sure you must be knowing. So limits are flipped. Now let us substitute the value. So j omega t naught by 2 minus e raised to the power of minus j omega t naught by 2 upon j omega. So again, I want to convert it to sine. So I will use this thing. This thing you know now. I will be using this again. Clear na class?
yes, ma'am.
Yeah. So I will multiply and divide by 2. 1, 2 comes here. 1 over here. So 2 times sine of omega t naught by 2 upon omega. Now I will again replace omega by 2 pi by t, the relation between angular frequency and the time period. So 2 sine 2 pi by t naught by 2 upon 2 pi by t. We will have some cancellations.
I think there would be any way to write this T as T naught also, right?
What?
Uh, I think there would be any way to write this T as T naught also. There would be might some relation.
No, no, no. We are not writing t in terms of t naught. T naught is a constant now. This constant.
Yes, ma'am. But it's period also, right? The
Yes,
whole
it is,
period is
but yes, you just see, you will get to know. So now we have this. I will put it inside a box, you know that it is not for this. So sine pi t naught by t upon pi by t. Now, since I want to convert it in terms of sync, so I will multiply and divide by T naught. I will just write the definition of sync here. So, sync of theta is sine pi theta upon pi theta. So, here I want to introduce a sync. So, what I will do is I will multiply and divide by T naught. Now, you see, this has become the sync function. So I can write it as T naught sync of T naught by capital T. Is this fine? This expression till here.
Yes, ma'am.
Now what I will do this time period, I will again write it in terms of angular frequency. So T naught sync, T will be 2 pi by omega, the same relation between the angular frequency and time period. So I will have T naught 2 pi omega comes here. So I have this. So now what I have is that the Fourier transform of my rectangular pulse comes out to be this sinc function. So this, okay, I will write it at the bottom. But before that, let us quickly look at sinc function one more time. So sinc of theta has zero crossing at every integer value of theta. Sinc theta is sine pi theta upon pi theta. So except for theta equal to 0, because that will be a 0 by 0 form and we will get a finite value. And at other values, whenever this theta is some integer, sine will be 0. So we will have 0 crossing for the sinc function. So we will have 0 crossing at every integer value of theta. So I will draw it here. It actually extends, you know the sinc function now. It does not die. Although the amplitude keeps on decreasing, but it extends from minus infinity to infinity. This is sinc theta. At here we have theta. So at 0, this value is 1. Then when theta is plus 1, it will be 0. Theta is plus 2, it will be 0. Plus 3, 0. And it keeps on extending. Similarly, minus 1, minus 2, minus 3, and so on. So this is the sinc function. Now we calculated this Fourier transform. I will write it here. So rect of t by t naught had the Fourier transform, we just calculated it here. So it is T naught sinc of T naught omega by 2 pi. So this is the Fourier transform we have. Now look at this. This signal over here, it is 1 between minus T naught by 2 to T naught by 2, and outside this interval it is 0. So can we say that it is finite in time?
Yes, ma'am.
Others, can we say that it is finite in time? Okay, now let us look at its Fourier transform. All right, I will draw it here actually. So following is the spectrum of rectangular pulse. x of j omega, and here I have omega. This is sync. So at 0, it will have this value T naught. Then uh, for the first 0 crossing, so this thing T naught omega by 2 pi over here, T naught omega by 2 pi, that will be equal to 1, theta equal to 1, T naught omega by 2 pi equal to 1. I'm just using this. Theta equal to 1, it is 0. That is the first 0 crossing on the positive side. So that gives me the value of omega to be 2 pi by T naught. And similarly, we will have 0 crossing at k times omega equal to k times 2 pi by T naught. Like this only, integers. So 0 crossings at omega is equal to k times 2 pi by T naught. So this first 0 crossing over here, this value is 2 pi by T naught. Then next, this was theta, 2 theta. So 2 times 2 pi by T naught. So 4 pi by T naught, and so on. Again, here in the negative side. This is clear now, the 0 crossing values.
Yes, ma'am.
So now what I want you to see, let us go back. This is finite in time. But what happens in the frequency domain? We get this. The sync, although its amplitude keeps on decreasing, but it keeps on going like this in both the directions. So it is finite in time and infinite in frequency. Now let us take ideal low pass filter, which will be in the form of rect, and then we will calculate its inverse Fourier transform. Now we will take ideal low pass filter. I'm drawing it here. So this is the midpoint 0, omega naught by 2, minus omega naught by 2, plus omega naught by 2, 1. So this is in a frequency. So here this is omega, and this is the Fourier transform. So basically what I'm saying is that this is in the frequency domain. And now can someone tell me how will we write it in terms of rect?
Rect
Yes,
T by omega naught.
omega by omega naught. Here the independent variable is omega. So just like in time we had t by t naught. Here the time was t by t naught. Similarly here we have omega by omega naught. So now we have rect of omega by omega naught, which is this function. This function. Now this is in frequency domain. I want to find out its inverse Fourier transform. So we will now use the inverse Fourier transform definition. According to that, xt is 1 upon 2 pi integration from minus infinity to infinity x of j omega, that is this thing in our case, e raised to the power of j omega t d omega. So this is the definition of the inverse Fourier transform. Now let us apply it to this. This is x of j omega here. So I have 1 upon 2 pi. It is non-zero in the interval minus omega naught by 2 to omega naught by 2. the value is 1 and outside it is 0. So I have this. Let us, do you want me to calculate this integral, or will one of you calculate and tell me?
We will calculate.
Okay, do it. So I will also write it down, but you don't look at the screen. You do yours, and then once you're done, you can see. So start, okay? Have you calculated?
Yes, ma'am. But I got 1 by pi t sine omega naught by 2 into omega naught. I think I have made some mistake in the last.
You got this now, the one in blue, the one encircled in blue.
Yes, ma'am.
Yeah, so this is correct. So once you
Uh,
solve now,
but
you,
ma'am, I have written in omega.
how can you write it in omega? The variable of integration is omega now. So when you substitute the limits, they will be for omega, not for t na. We substitute for the variable of the integration na.
Yes, ma'am. Yes, ma'am.
Okay.
We will change this t as omega not by t or omega as omega.
Okay, now I will start explaining. So please listen. So we had this Fourier transform. We want to find its inverse Fourier transform. So we use this definition of the inverse Fourier transform, which is xt is equal to 1 upon 2 pi integration from minus infinity to infinity x of j omega e raised to the power of j omega t d omega. So this x of omega is given here. So it is 1 between minus omega naught by 2 to plus omega naught by 2. Outside it is 0. So I wrote 1 here. I had these limits. Now I'm left with this. So I integrate 1 by 2 pi remains as it is. Integral of e raised to the power of j omega t with respect to omega, that is d omega. So I get this j omega e raised to the power of j omega t upon j t. The limits are minus omega naught by 2 to plus omega naught by 2. So I write 1 by 2 pi. I put the limits. Upper limit j omega omega naught by 2 into t by jt. Lower limit minus omega naught by 2. I get this term. And this was the common denominator. So this is what I have. Now the thing which is inside green, we can write it as sine. just the sine theta that we used earlier. Sine theta is a raised to the power of j theta minus e raised to the power of minus j theta by 2j. So the one in green becomes sine omega naught by 2 into t, and this pi t that was left. So now we have this. I want to write it in terms of sinc function. So what I will do for sinc, I need pi. So if I multiply by pi, I have to divide by pi. So this is what that happened inside sine. Now in denominator, I want this same thing. So I pi t was already there. So I had this term extra. So I divided and multiplied by this same term. Now this becomes sinc. So this sinc comes here, and this is the amplitude. So now is this integral clear? How we got this integral?
Yes.
Now what I want you to see is that in frequency domain, if we have this rectangular pulse which is finite, that is it is finite in frequency, then in time we get sinc which is infinite in time. So this is what the uncertainty principle is, that if you have finite time length, then you will have infinite bandwidth, and if you have finite bandwidth, you will have infinite time length. So this is the uncertainty principle. I will just quickly write it down. Finite time length leads to infinite bandwidth. If I take the rectangular function in time, then in frequency we get sinc, which is infinite. So finite time length leads to infinite bandwidth. If I have finite bandwidth, that is the low pass filter. So in frequency it was finite. So in time we got sinc function, which was infinite. So infinite time length. So this is what uncertainty principle is. Is uncertainty principle clear?
Yes.
Now we will move to the properties of Fourier transform. So I just before that, a quick thing I want you to notice. I have a time domain signal xt. The Fourier transform is x of j omega. X of j omega, the Fourier transform is given by integral minus infinity to infinity xt e raised to the power of minus j omega t dt. Now if I take omega is equal to 10 pi, that is x of j 10 pi, then I will get some number here. So what this denotes is, now it denotes frequency component that is present in the signal xt, frequency component that is present in the signal xt, corresponding to the phasor with frequency 10 pi. Corresponding to the phasor with frequency 10 pi. So I had this x of j omega, the Fourier transform. If I take omega is equal to 10 pi, then this x of j 10 pi, this will denote frequency component present in xt corresponding to the phasor with frequency 10 pi. So I just wanted you to notice this. Now let us start with the properties of Fourier transform. And you will kind of see a lot of similarity between the Fourier series and Fourier transform properties. So let us begin. Properties of Fourier transform. So I have this xt, which is time domain, x of j omega, which is in frequency domain. And we will also see the effect on bandwidth. Very similar to the Fourier series case. Now, the first property involves a conjugation. So the time domain signal xt, when we conjugate it, then what happens in frequency domain? So here the signal xt has a Fourier transform x of j omega. When we conjugate it, then in frequency domain, there is conjugation and there is also reversal. So this was there in Fourier series coefficient also. I will just quickly scroll up to show you. Yeah, look at this. When we conjugate in time, conjugation and reversal, and the bandwidth does not change. So you will see these properties are very similar. So x conjugation in time, in frequency conjugation and reversal, bandwidth does not change. Now next, reversal in time. Reversal in time results in reversal in frequency. Again, bandwidth does not change. Then x of t plus minus s, that is time shift, delay, advance, both. So it becomes x of j omega e raised to the power of plus minus j omega s. So here I want you to notice that when here plus is there, then in frequency domain we have plus. When minus is there, then minus is there. Just like in the Fourier series case. This is clear.
Yes.
Now there is this property xt plus minus j nu t. So here a shift in frequency happens. So x of j omega minus plus nu. So here the sign changes. When I have plus here in frequency, there is minus. When I have minus here, there is plus. This was also the case in Fourier series also. So in these two also now, the bandwidth does not change. Only the phase changes in the other domain. So for this case, the phase changed in frequency. For this case, the phase change happened in time. I will write down that statement. No change in bandwidth. Only phase change in the other domain. Now the last case of time scaling is left. I will write it here. Yeah. So now x of ct, time scaling. X of j omega by c upon mod of c. So omega by c and division by modulus of the same constant. So same as there, if c is greater than 1, it expands. If c is less than 1, then the bandwidth shrinks. So if c is greater than 1 if in x of ct, if c is greater than 1, then we know it compresses. But in frequency, when c is greater than 1, it expands. So if in time it is compressing, frequency it will expand. If in time it is expanding, then in frequency it will shrink. So that is what is written here. Now another thing I want you to notice is that in this time scaling thing over here, the density will change, but the area will remain fixed. Let us see why is that. So density changes, but area remains fixed. So what I'm saying is, so this is in, I'm drawing this in frequency. So this is the one where this is like the spectrum corresponding to x of t. Now the spectrum corresponding to x of ct. So here the spectrum has shrinked. So in time there must have been expansion. So what times or if the spectrum expands, if spectrum expands, then in time there must have been compression. So what I'm saying is the area of this under this black rectangle is equal to the area area under black triangle is equal to area inside the red, which is equal to area inside blue. So that is what I mean by when that density changes but area remains fixed. Now I will quickly show you why is that. So let us go back to the inverse Fourier transform definition. X of t is 1 upon 2 pi integration from minus infinity to infinity x of j omega e raised to the power of j omega t d omega. This is the definition of the inverse Fourier transform. Now I want you to put t equal to 0 here. When we put t equal to 0, I get x of 0 is equal to 1 upon 2 pi integration minus infinity to infinity x of j omega. And when we put t equal to 0, e raised to the power of j omega into 0 will be e raised to the power of 0, which will be 1. So when we put t equal to 0, this is what we have. Is this clear?
Yes, ma'am.
Now, this term x of j omega d omega integration from minus infinity to infinity, this is actually the area under the spectrum, right? Are you able to see this? The area under the spectrum is this only. These both things in the green and circle are the same.
Yes, ma'am.
Yes, ma'am.
Now, um, either we take x of t or we take x of ct. When we put t equal to 0, what we will get is x of 0 only, right? When either we take xt or x of ct, the scaled version, we put t equal to 0, we are going to get x of 0 only, right? Class, are you able to see this?
Yes, ma'am.
So x of 0 is same for x of t and x of ct. So x of 0 should not change. It is same. So it should not change. So if x of 0 is same, so let us come back here. X of 0 into 2 pi, which is equal to this, will also be same. Are you able to follow this? X of 0 is same for both of them. 2 pi is a constant. So this will be same for both of them. And this is what? What is this? The area of this spectrum. Hence, we can say that density changes but area remains the same. So this is how we can say that area will be same or area should not change. Is this clear why area is same here in this property? The last one, time scaling.
Yes, ma'am, clear.
Okay, now the next are the properties related to symmetry in Fourier transform, just like we had in Fourier series. Symmetry in Fourier transform. So xt we have it in time domain. X of j omega we have in frequency domain. This is also, you can find this analogy from the Fourier series. So if in time xt is even, then in frequency x of j omega will also be even. If x of t is odd, x of j omega will be odd. If x of t is conjugate symmetric, then x of j omega will be real. If x of t is conjugate antisymmetric, x of j omega will be imaginary. Now, if x of t is real, x of j omega will be conjugate symmetric. If x of t is imaginary, x of j omega will be conjugate antisymmetric. So you see, even, odd, odd. If here it is conjugate symmetric, here it is real. If here it is conjugate symmetric, it is real. Here conjugate asymmetric, imaginary. Here imaginary, conjugate asymmetric. And this was also the case in the Fourier series also. Are these properties clear? The derivation of these properties, for that you can refer to professor's lectures. What the properties are, is that clear?
Yes, ma'am, clear.
All right. Now let us take a look at another thing. So xt can be written as x of r, the real part, plus j times x of I, the imaginary part. And we can also write x of t in terms of its conjugate symmetric plus conjugate asymmetric part. This is clear now. You know this now. All right. Now let us take real part of x of t. So if we want to write the real part of x of t, it is equal to x of t plus x conjugate of t divided by 2. This is how we write the real part of any complex number. So this is what we have. Now let us take the Fourier transform of this. So x of t will have the Fourier transform x of j omega. X conjugate of t from this property will have the Fourier transform x conjugate minus j omega. So that is what I will be writing here. X conjugate minus j omega and divide by 2. So this linearity property, that if this is added or scaled by some constant, will also happen here also. Now this x of j omega plus x conjugate minus j omega by 2, this is the conjugate symmetric part of x, the Fourier transform. Do you remember how we used to calculate the conjugate symmetric and conjugate asymmetric part of any signal? Are you able to recall that?
Yes, yes, ma'am.
So that is what we have used. So now what we saw was, when we take real part of this, we get the conjugate symmetric part of the Fourier transform. Now let us see what happens if we take imaginary part of the time domain signal. So imaginary part of xt, how do we write the imaginary part of any complex number? That number minus its conjugate divided by 2. That is how we write the imaginary part of any complex number. Now let us again calculate the Fourier transform for this. X of t has x of j omega, x star of t, just like here, we'll have x star minus j omega. So this is the capital X. You are able to differentiate between capital and small x here now.
Yes, ma'am.
So now the Fourier transform of imaginary part comes out to be this, and this is what is actually the conjugate asymmetric part. This is how we calculate the conjugate asymmetric part. So what did we observe? When we take the real part of this, we get the conjugate symmetric part of Fourier transform. And when we take imaginary part, we get the conjugate asymmetric part of Fourier transform. Now let us see if we take the conjugate, if we take the real part of Fourier transform, then what do we get in the time domain? Let us see that now. Or maybe we can alternatively take the conjugate symmetric part of x. Can someone tell me what will this be equal to?
xt plus x star minus t.
Divided by 2.
Yes, ma'am.
So this is the conjugate symmetric part of xt that we saw in the very beginning lectures. Now let us again find the Fourier transform. So we knew that the Fourier transform of x conjugate of t is conjugation and also reversal. Now if I take this reversal here, then this will be x star of j omega. Is this clear? The one inside red? All right. So let us now write the Fourier transform of x, Fourier transform of x of conjugate symmetric part of xt. So we have x of j omega plus x star j omega from here divided by 2. What is this? This is actually the real part of the Fourier transform. So this is real of x of j omega. So if we take the conjugate symmetric part, we get the real part. So that analogy is coming here also. Now let us take the conjugate asymmetric part of x. So will someone tell me what will that be equal to? The conjugate asymmetric part?
xt minus x star minus t by 2.
Yes. This is how we find the conjugate asymmetric part. Now let us find the Fourier transform of this. X of t will have x of j omega minus x star of minus t. So this had x conjugate j omega, the capital X. So this is what we have. And what is this equal to? This is equal to the imaginary part of x of j omega, right? Is this fine, class?
Yes, ma'am. Fine.
Now let us like write it down in one place. So x of t is equal to xr plus j times x of I, which can also be written as conjugate symmetric and conjugate asymmetric. Similarly, its Fourier transform has some conjugate symmetric and some conjugate asymmetric part, and it can also be written in terms of real and imaginary parts. Now, if I find the Fourier transform of the real part of time domain signal, I get the conjugate symmetric part of the Fourier transform. And if I calculate the Fourier transform of imaginary part of xt, I get the conjugate asymmetric part of the Fourier transform. So this is what these arrows are indicating. Now, similarly, if the real part of the Fourier transform is taken, then that corresponds to the conjugate symmetric part. And similarly, when the imaginary part of Fourier transform is taken, it corresponds to conjugate asymmetric part. So in the red one, we are calculating inverse Fourier transform, blue one, the Fourier transform. So this thing over here is just the summary of what we did here just before this. Is this fine?
Yes, ma'am. Fine.
Now the next thing is duality property of Fourier transform. So I will quickly state that property for you here. Duality of Fourier transform. Suppose I have a time domain signal xt and I find its Fourier transform. That will be denoted by a capital X of j omega. This is capital X of j omega. So if just some example waveform, if this is in time, the rect one, then in frequency we get sync. We have been seeing that since the beginning of the class. So this is omega. Now what I do, I instead of this omega, I consider it to be in time. So what I have is something like capital X of jt. So I just replace that omega by t. Now I find the Fourier transform of this. This is when the duality property comes into picture. Now I find the Fourier transform. So do you know what do I get? 2 pi times small x of minus j omega. So this signal comes here with this scale factor and reversal. So if I were to draw it, then what I will have over here is this 2 pi, and here it will be omega. Or maybe I can draw it with red for better correlation. Since this is even, so minus omega will make it the same only. So this is what is the duality property is all about. If uh, if xt has a Fourier transform capital X of j omega, then capital X of jt will have the Fourier transform 2 pi small x of minus j omega. That is this same signal with this kind of modification. So is the statement of duality property clear?
Yes, ma'am. Clear. It just, ma'am, scaled or something that way.
Scaled and time reversal, scaled and reversed, but notice here t, here it has omega. This one here has omega and I replaced it by t.
Yes, ma'am. Got it.
So let me also write something textually. So if capital X of j omega is the Fourier transform of small x of t, then 2 pi times x small x of minus j omega is the Fourier transform of capital X of jt. Or we can say the inverse Fourier transform of x of j omega is a capital X of minus t divided by 2 pi. So let us see. Fourier transform of x of t is capital X of j omega. Now I want to find the Fourier transform of this function that I got. So that is equal to, by the property, 2 pi small x minus nu. The t I just wrote it minus nu. Now I bring this 2 pi on the left hand side. So I have x of minus nu. Now I will take this minus sign inside omega. I get x of nu. So the inverse Fourier transform of x of nu is x of minus j omega by 2 pi. Let me make it more clear with an example. Just I am taking the same example that I have taken here, just writing it one more time. So what I'm saying is, suppose I have rect t by t naught in time. I find its Fourier transform. Then it comes out to be a sinc function, t naught omega by, this is I just took it from what we discussed in the starting. So when I take this rect function, I get this sinc function as the Fourier transform. Is this clear?
Yes, ma'am, it's clear.
Now, according to duality property, what I'm saying is, if I this Fourier transform function, I take it, but I replace this omega by t. So what do I have? T naught sinc of t naught. I replace omega by the time. So if I take this function now, then what will be the Fourier transform of this? So that is given by the duality property. And according to that, it will be 2 pi times minus of this function. I mean, sorry, let me write it down. Rect of minus omega by t naught. This is what duality property states. Are you able to see this now?
Yes, ma'am. We have just to multiply by 2 pi and take a
Reverse.
reversal with minus omega in
Yeah.
place of.
So I have this function. I find out its Fourier transform. Now in this Fourier transform, omega is replaced by t. Then if I have this, then duality property says that the Fourier transform will be 2 pi times this function with a reversal. So this is what duality property states. Is the statement of duality property clear?
Yes, ma'am, clear.
So why do we have this duality property? What is its use? So it is the following. If I have this duality property, then if I'm implementing something somewhere, then I don't need to have blocks for Fourier transform and inverse Fourier transform. What I can do, I will just use the Fourier transform and just change the axis. So it will reduce the complexity of my hardware. Is the application clear? I will just write it down for your reference. So no need for both Fourier transform and inverse Fourier transform blocks. Only a Fourier transform block is needed. It reduces hardware complexity. That is why. So this was about the duality. Now next we have the convolution and Fourier transform. So what happens if we convolve in time and convolve in frequency? The property related to that. That is our next topic. Convolution and Fourier transform. So I will write it in time domain and frequency domain. So if in time domain my signals are multiplied xt into yt, the Fourier transform of xt is x of j omega. The Fourier transform is y of j omega. So if in time domain I multiply them, then in frequency domain there is convolution and a scale factor of 1 by 2 pi. In time domain multiplication, frequency domain x of j omega convolved with y of j omega upon 2 pi. And if in time domain I convolve, that is xt convolution yt, in frequency domain, straight away multiplication of their Fourier transforms. Now what I want you to notice is, and we will also see example to understand it better, when in time domain they are multiplied now, then in frequency we can get larger bandwidth. Larger bandwidth, that is new frequency components can come. New frequency components can come. And if if in time domain there is convolution, then we get a smaller bandwidth because here it is multiplication, so only the common frequency components will come. So this will give us smaller bandwidth, or we can say only common frequency components will come. So first I will give you the example of this convolution. So x of t convolved with yt, that in frequency domain is just the multiplication, you can see x of j omega times y of j omega. I will draw three of them. So this first one corresponds to x of j omega. The bandwidth, I can say that it is by. It is some random Fourier transform, anything. Now the second one corresponds to y of omega. The bandwidth I can say d of y. So another random function. Now over here I have the multiplication of x of j omega and y of j omega. So when we multiply them, are you able to see that we will only get the common part, other and the rest of the part will be zero because of the multiplication?
Yes, ma'am. The remaining part will multiply 0 and give us 0.
Others are also able to see this. I just want to make it more clear. So the resultant that we will have will just be the multiplication of them. This will become 0. So if this bandwidth is B, then can we say that B will be less than equal to minimum of Bx and By? At max, it can be equal to the minimum or less than equal to their minimum. Is this clear?
Yes, ma'am, clear.
So when in time there is convolution, that is multiplication in frequency, then we get a smaller bandwidth, only common frequency components come. Now let us look at the case when they are multiplied in time. So this is for x of t into y of t. Suppose I take x of t to be equal to e raised to the power of j pi t, and yt to be e raised to the power of j 2 pi t. Can someone tell me what will be x of t into y of t? A class, I have this x of t and y of t. When I multiply, what will I get?
E power J3 pi t.
Yes, e raised to power of j pi 3. I will just very quickly write down this. So we multiply them. When the exponentials are multiplied, the powers get added. So j pi t plus j 2 pi t, that is j 3 pi t. So this is what we get. So now this is for x of t, this is for y of t, and this is for their multiplication. So x of t had this impulse kind of at pi, y of t had this impulse kind of thing at 2 pi. X of t, y of t. This is x of t into y of t. This will have it at 3 pi. So what do we see? This 3 pi component which was present neither in this nor in this has come in output. So we see that new frequency component has been added. So this is what it states. When we multiply the larger bandwidth, new frequency components can come. So this is how it is. So that is all I had from my side to discuss today. Are there any doubts? Class, does anyone have any doubt or we can close now?
No, ma'am. Uh, Take example of that area uh, in earlier that you have talked about.
This one.
No, uh,
Which one?
scroll up, ma'am.
Are you
Yes,
talking about this
yes,
property?
yeah, yes.
So this is a property, na? So this is valid for any signal. So okay, maybe we can take rect t only. You wanted an example for this, na?
Yes, ma'am.
So for example, for this, that air density changes but area remains fixed. Example for this or this property.
The property, ma'am, that is scaled by C.
Okay. So rect of t by t naught had the Fourier transform. What was the expression? Let me just look back. Yeah,
T naught sync T naught omega by 2 pi.
sync t naught omega by 2 pi. Let me just copy paste the property statement over here. Yeah. So this is what the property stated. So let us take maybe rect of 4t by t naught. So this is if x of t is equal to this, then this is equal to x of 4t. Is this fine, Abu?
Yes, ma'am.
So by the property, we can say that the Fourier transform of this will be, so C is 4, mod of C will be 4 only. So 1 by 4, T naught was constant, it stays as it is. Then sinc of T naught, omega is replaced by omega by C. So it will be replaced by omega by 4, right? So omega by 4 and this. So we can simplify to be it equal to T naught by 4 sinc of omega T naught by 8 pi. Is this fine? Is this clear?
Yeah, ma'am. Clear. Got it. Here we have to just put at T naught by 4, yeah, T naught by C in place of CT.
So this is 1 by mod C and this is omega by C. So if my Fourier transform had more omega terms now, so every omega will be replaced by omega by C, and this mod C will just be the scaling of the amplitude.
Okay, ma'am. Got it.
Okay, so are there any other doubts?
No, ma'am.
All right, then let's end the session. Thank you for joining. On Saturday, we will be discussing problems based on week 9 theory. So all these things will be covered. Please try to watch week 9 videos by Saturday. So, okay, good night. Bye bye.
Thank you,
Thank you,
ma'am.
ma'am. Good night, ma'am.
Good night. Good night.